Hello. In this video, we are going to discuss critical behavior in the van der Waals gas, and we are going to derive the critical constants. Now we plot three typical isotherms for a gas that satisfies the van der Waals equation of state. Above the critical temperature, the isotherm looks almost exactly like the ideal gas isotherm. At the critical temperature, we get an isotherm that has sort of a plateau, a mesa, at the critical temperature. So this is the point, the critical point, where the first derivative is equal to 0 and the second derivative is equal to 0. So this is the isotherm at the critical temperature, which we might call the critical isotherm. And then below the critical temperature, we see a wiggly up and down pattern. And when we see these types of so-called van der Waals loops, we realize that they are unphysical. Unphysical is another way of saying is unrealistic, because we see that in this particular region here, as we increase the pressure, the molar volume increases, which is not reasonable. So, but we can use the fact that we have these van der Waals loops at certain isotherms as a reminder that these particular isotherms are for situations where we're below the critical temperature. This is, the black is at the critical temperature, and then the orange is above the critical temperature. When we reach the critical point, we know that several things must be true. We know that the first derivative of the pressure with respect to the volume is equal to 0. We also know that the second derivative of the pressure with respect to the molar volume is 0 also. Similarly, we know that at the critical point, the temperature is the critical temperature, the pressure is the critical pressure, and the molar volume is the critical volume. The van der Waals equation of state can be written as the pressure equals RT divided by the molar volume minus the constant B minus A divided by the molar volume squared. And I'm going to write this very slightly just to make differentiation more straightforward. So we can write this as RT times the quantity, the molar volume minus B, to the minus 1 power, so just writing this as an exponent, minus A times V times the molar volume to the minus 2. Next, we want to differentiate this expression for P with respect to the molar volume. And we use the rules for exponents, that we bring the exponent in front as a multiplier, times RT. R and T are both constants in this differentiation. And then we have V sub m minus B to the minus 2nd power. Then using the chain rule times the derivative of V sub m, but this is just equal to 1. And then for the second term, the minus 2 multiplies the minus sign in front, so we get a plus 2 times A. And then we decrease the exponent by 1, so it goes from minus 2 to minus 3. This is exactly equivalent to minus RT divided by V sub m minus B quantity squared plus 2 times A divided by the molar volume cubed. Next, we find the second derivative of the pressure with respect to the molar volume. And we use the fact that the second derivative is the first derivative of the first derivative. So we use the properties of exponents. We use the minus 2 as a multiplier. We bring that in front as a coefficient. Minus 2 times minus 1 gives us a plus 2. So we have 2RT times the quantity V sub m minus b to the minus 3, and then times 1. So I'm leaving out the 1 just to save a little space. And then we have minus 3 times plus 2 gives us minus 6a, and then remember we decrease the exponent by 1, so minus 3 becomes minus 4. And this can be written more conventionally as 2RT over the quantity V sub m minus b cubed minus 6a divided by the molar volume to the fourth power. The expressions for the first and second derivative are true under any circumstances, and at the critical point, we know that the first derivative is equal to 0, and the second derivative is equal to 0. A trick that we will use now is to rearrange each of the expressions, the equation in blue and the equation in purple, in terms of RT, which will simplify the algebra tremendously. So if we add RT plus Vm minus b, the quantity squared, to each side, we get that 2a divided by V sub m cubed is equal to RT divided by quantity V sub m minus b squared. Now we simply multiply each side by the quantity V sub m minus b squared, and we get that RT, in this case, is equal to 2a times the quantity Vm minus b, the quantity squared, divided by the molar volume cubed. Similarly, we can use our expression in purple, which we obtained from evaluating the second derivative at the critical point. We can add 6a divided by V sub m to the fourth power to each side, and that gives us 2RT divided by quantity cubed equals 6a divided by the molar volume to the fourth power. And now, if we multiply each side by this expression, we get that 2RT equals 6a times the molar volume minus b cubed divided by V sub m to the fourth power. And then we immediately recognize that we can divide through by a power of 2, and we get that, in this case, that RT is equal to 3a times V sub m minus b cubed divided by the molar volume to the fourth power. We then recall that RT is certainly equal to RT. So we can set this particular expression for RT, so that's our 3 times a V sub m minus b cubed divided by the molar volume to the fourth power is equal to 2a times V sub m minus b squared divided by the molar volume cubed. We can cancel the a's from each side, so that particular constant drops out. And we can multiply each side of the equation by the molar volume to the fourth power. And that gives us, on the left-hand side, you have 3 sub m minus b cubed equals 2 times the molar volume times molar volume minus b, the quantity squared. And then we can cancel from each side. And that gives us 3 times the molar volume minus b equals 2 times the molar volume. We can expand the left-hand side using the distributive law, and we get that 3 times the molar volume minus 3b equals 2 times the molar volume. We can add 3b to each side, and we're going to get that the molar volume is equal to 3b at the critical temperature. So that gives us that this is also the critical volume. So that gives us the first of our critical constants for the critical volume, and we see that it is equal to 3b. Recall that we had determined the first derivative of the pressure with respect to the molar volume, and that we had found that to be minus RT squared plus 2A divided by the molar volume cubed, and that this is equal to 0 at the critical point. Next we add RT divided by this quantity squared to each side, and that gives us that 2A divided by the molar volume cubed is equal to RT divided by B sub m minus B, the quantity squared. Next, at this point, we want to use the fact that the molar volume, we have an expression for that at the critical point, so we're going to let the molar volume equal 3b and substitute that into our expression for the first derivative. Once we do that, we get A divided by the quantity 3b cubed equals RT divided by 3b minus b, so that's 2b squared. Simplifying, we get that 2a divided by 3b cubed is going to be 27b cubed equals RT divided by 4b squared. Next we add RT divided by this quantity squared to each side, and that gives us that 2a divided by the molar volume cubed is equal to RT divided by B sub m minus B, the quantity squared. Next, at this point, we want to use the fact that the molar volume, we have an expression for that at the critical point, so we're going to let the molar volume equal 3b and substitute that into our expression for the first derivative. Once we do that, we get A divided by the quantity 3b cubed equals RT divided by 3b minus b, so that's 2b squared. Simplifying, we get that 2a divided by 3b cubed is going to be 27b cubed equals RT divided by 4b squared. Now we multiply each side of the equation by 4b squared, and that gives us 8a over 27b is equal to r times t. Now we divide each side by the gas constant r to get that the temperature, which is the critical temperature because we're at the critical point, is equal to 8a divided by 27br. And this is the second of our critical constants for the van der Waals gas. Recall that the equation of state for the van der Waals gas is equal to RT divided by B minus A divided by the molar volume squared. So to find the value for the critical pressure, we substitute the value for the critical temperature and the value for the critical volume into the van der Waals equation. So more explicitly, I can write it this way, that the critical pressure is equal to R times the critical temperature divided by the critical volume minus B minus A divided by the critical volume squared. So what we're going to do now is to substitute this expression for the critical temperature into the van der Waals equation and the expression for the critical volume. So let's see what that gives us. We get that the critical pressure is equal to R. So we substitute the critical temperature here, which is 8A divided by 27BR divided by the critical volume, which we know is 3B minus B, so that just gives us 2B in the denominator, minus A, and now we have the critical volume squared. We know the critical volume is 3B, so that's 3B squared. And this simplifies considerably. The gas constant R drops out. And this becomes 8A 27BR times 2B minus A divided by 9B squared. This becomes 8A divided by 54B squared minus A divided by 9B squared. And recall that to add or subtract fractions, they have to have the same denominator, so this is equivalent to 8A divided by 54B squared minus 6A divided by 54B squared, which gives 2A divided by 54B squared, which reduces to 2A, reduces to A divided by 27B squared. And this is our critical pressure. So, in conclusion, we began with the equation of state for the van der Waals gas. We determined the first and second derivatives of this expression of the pressure with respect to the molar volume. We set those derivatives each equal to 0, and then solved for the volume, temperature, and pressure, which at that point are the critical pressure, the critical temperature, and the critical volume. I thank you very much for your attention. Have a good one.